Hello and welcome. Three fonts walk into a bar and order drinks. The bartender gives them a hard look and says, "We don't serve your type here." In this video, we're going to learn the second of two integration techniques. This one is called integration by parts. Let's get started. You'll notice the font we have is, never mind. So we're going to first start by deriving the integration by parts formula. We're going to start by writing the product rule for derivatives. So the derivative of f of x times g of x is f of x times g prime of x plus g times f prime of x. This is one way to write the product rule. Usually we would go first times derivative of second plus derivative of first times second, but we can switch these two products around. Now we're going to play around with it a little bit. We're going to integrate both sides. So we're going to integrate both sides. And the integral of the derivative, remember we said those two undo each other. So we just get f of x times g of x. And then we'll have the integral of the right-hand side. Now what we're going to do is just switch the two sides of the equation. So nothing much right here. Nothing up my sleeve, nothing up my sleeve. We're just switching the two sides of the equation. The integral goes on the left. The f times g goes on the right. And then we're going to break up this integral into two integrals, the integral of the first term plus the integral of the second term. Just like with derivatives, integrals can distribute to term by term. They can apply to each term in a summation or with pluses or minuses. So then all we're going to do is take one of these integrals here, the second one, and subtract it over to the right side. Now it seems like all we've done is just mess around with some algebra, but it turns out at the end what we have is a super useful formula, the integration by parts formula, that's going to help us turn integrals that we can't do into integrals that we can do. Just to clean this up, because there's a lot of parentheses x's, we're going to let u equal f of x and v equals g of x. Not doing a substitution, well, some kind of a substitution, but we're just changing the variables around a little bit, changing the names. So then du equals f prime dx and dv equals g prime dx. So if you make all those replacements, then you have u, so f of x is u, and then g prime of x dx is dv. And then we have uv equals uv minus the integral of g of x here turns into v, and then f prime of x dx turns into du. So the integral of u dv equals uv minus the integral of v du. That's the integration by parts formula. Let's see how we can use it in example 1. We're going to start by looking at this example 1, integral of x sine x dx, and breaking up the integrand, as it's called, which is the inside of the integral. We'll talk about all those the vocabulary words in the future video. We're going to break up that into two parts. We're going to write we're going to let u equal x, so that's what we're going to call u, and then the rest of it is going to be the dv, so that our integral is of the form the integral of u dv, where u is x and then the dv is sine x dx. So that's the first step, is to identify what your u and your dv are going to be. Now the next thing we're going to do is figure out what we need on the right side of the integration by parts formula. We already have u, that's just x. We need to get v. So to get from dv to v, we're going to have to integrate. Then we also need v for here, and we also need du, which is the derivative of u. So let's first start by writing u equals x, and then dv equals sine x dx. So we need to figure out what du is. That's one part of it. Let's do that first. We're going to take the derivative of u, and we'll get the derivative of x is 1, and we have a dx here, just like we did when we were doing the substitution method. But then, unlike the substitution method, we've got this dv here, and we want to integrate, so find the antiderivative to figure out what v would have to equal. So antiderivative of sine x would be negative cosine x. Turning back around, if we had v equals negative cosine x, the derivative would be dv equals sine x dx. So now we have all of the parts that we need. We have the u, we have the v right here, we've got the v over here, we've got the du. In fact, if we wanted to write out in order of what we need, it would be uv, so uv, minus the integral of v du. This just helps you visually see what things you're putting together on the right side of the integration by parts formula. So this integral of u dv, by the integration by parts formula, is uv, which is x times negative cosine x, minus, that's this minus symbol here, the integral of v du. So v is negative cosine x, the du is just dx. So we've taken this integration by parts step, and let me identify each of these. This is uv minus the integral of v du. One thing to notice is that we never really changed variables. So unlike the substitution method where we changed the variable x into an integral that was all in terms of u, here we're never changing the variable of the integral. But we are changing the integral to a different integral for sure. We're just not changing the variable. Now hopefully that new integral is easier to handle, and it turns out it is. Before we do that integral though, let's try to clean up a little bit. We can write the negative in front. We have negative x cosine x. And then this negative one in front of the cosine x can come out of the integral and multiply to this negative one in front of the integral. And we just get positive 1. So plus the integral of cosine x dx. So this integral is definitely easier to do. We can integrate cosine x. The integral of cosine x would be sine x. And then we just add a little plus c because we've finished integrating. And if we go and take the derivative of negative cosine x plus sine x, we're going to get x sine x. Let's just do that off to the side for practice. Derivative of negative x cosine x plus sine x. Watch, it doesn't work. Math is falling down. Okay, let's find out. It seems like it won't work because look at this. We have two terms here, and how's that going to simplify to just x sine x? But let's see. So here we would have negative x times cosine x. The derivative there, we would need the product rule. So here we're checking our work. We're going to do first times the derivative of the second, plus the derivative of the first, which is negative 1, times the second, and then plus the derivative of sine, which is cosine. We're checking our work. So we have x sine x, and then look at this. Negative 1 cosine x is negative cosine x, plus cosine x is going to cancel. So actually x sine x is it. We're done. And that's exactly what we started with, was x sine x. So the antiderivative of x sine x, or the integral of x sine x, is negative x cosine x plus sine x plus c. Now if we had chosen a different u and dv and run those through our integration by parts formula, it wouldn't give us a new integral that was simpler to integrate. Let's see what it looks like in that case. Let's say that we switched the x and the sine x around so that we're going to identify the sine x as the u and the x dx as the dv. And then over here we're going to write so I get for doing two things at the same time. We're going to write u equals sine x, dv equals x dx. Those are the two parts right here of our integral. So now finding our du by taking the derivative of sine x, we'll get cosine x dx. Integrating the dv, integrating the x, we'll get x squared over 2. Now here you don't have to put the plus c. That one we only are interested in the plus c with our integral over here. So then here we would write uv minus the integral of v du. uv, that's sine x times x squared over 2 minus the integral of v du, x squared over 2 cosine x dx. So this is, if you use the integration by parts formula, this is what you would get. And you can take this step just fine. That's okay to do. The formula still holds true no matter what the u and the dv that you select. But this new integral seems like it's harder to do than the original one. I mean, we went from an x sine x to now an x squared cosine x. So it turns out that doing integration by parts here gave us an integral that was harder to do. It made it worse. It changed the exponent of 1 of the x from 1 to 2. It just made things worse. So this way of using the integration by parts just didn't seem to work out very well. The choice of u as being x was better than letting u equal sine x. So the goal here is to turn the integral of u dv into one that you can't do, into an integral of v du, that's the new integral you'll have, into one that you can do. So you're going to turn the integral of u dv into this integral of v du, and hopefully you can do the integral of v du. Hopefully that's a simpler integral to handle. So just like with the substitution method, you're trying to make a substitution that makes your new integral simpler to integrate. Same thing with integration by parts. You're trying to choose your u and your dv so that when you apply the integration by parts formula, the new integral, which is the integral of v du, is simpler to integrate. Now there's a mnemonic that can help you figure this out, and it's called liate. It turns out that liate goes back to, let me see, I wrote it in my notes here, 1983. 1983, this guy named Herbert E. Kasube wrote this article called A Technique for Integration by Parts in the American Mathematical Monthly back in 1983. And I guess it's issue 90 and pages 210 to 211 if you really want to go look it up. So this is where the liate mnemonic started. And this is just a mnemonic. It's not like a special technique or anything. It's just a helpful mnemonic, a helpful way of remembering what a good choice for u is in the integration by parts formula. So I'm going to write it like this, so it's a little easier to see. I'm going to write it vertically, liate. So the L stands for log. Logs are the good, best choice for you as a first choice. So logs like ln of x, log base a of x, and so on. The I would stand for inverse trig. These would be things like inverse sine, inverse cosine, and so on. That's the next best choice for you if you can do it. The reason for this is that the derivative of log is 1 over x, and that's simpler than the log function itself. The 1 over x can interact with other expressions, possibly canceling off the factor of x. And as a preview, as a hint or a foreshadowing, we're going to see that happen when we integrate ln of x. Inverse trig functions, same kind of thing. The derivative of inverse sine of x is 1 over the square root of 1 minus x squared. And even though that is complicated because it has a square root, sometimes that can help you take a step further. A stands for algebraic functions. And here this means actually like polynomials, like x squared plus 3x minus 1, for example. those would be the next best choice for you because they get simpler as you take the derivatives of polynomials. Then T stands for trig functions. This would be like just regular sine and regular cosine and tangent and so on. And E stands for exponential functions like e to the x, a to the x. I guess that pretty much covers it. Actually, a to the x covers everything. Okay. So trig functions and exponential functions are generally bad choices for you because when you take their derivatives, they don't get any simpler. The derivative of sine is cosine. The derivative of cosine is negative sine. They just keep going back and forth. The derivatives of exponentials just stay the same. They don't get simpler. And we want simpler du's because that's what's going inside of your new integral, right? The new integral will be the integral of v du. You want your du to be simpler, or at least to be able to interact with v and simplify. So this is, again, a mnemonic for helping you determine a good choice of u if you're looking at an integral and you're thinking about using integration by parts. Let's apply that to example 2. Here we have the integral of ln x dx. Now, really, the only choice for u we have here is ln x. I mean, I suppose you could let u equal to 1, but that's not going to be super duper helpful. So here, the only choice you have for u is ln x. So let's let u equal ln x. The dv will be all the rest of it, which is just dx. There's not much left. Let's write up u equal ln x, dv equals dx. Now we're going to take the derivative of u and we'll get 1 over x dx. And then integrate v, the integral of 1 is going to be x. Integral of 1 will be x. Now we're going to pull out of this integration by parts. The right side of the integration by parts formula. We're going to have uv minus the integral of v du. And by the way, this is definitely one to commit to memory. It comes up so often, and we'll show a different way of writing this so that you don't have to remember all the u's and the dv's. But this is definitely a formula that is going to come in handy for not just this class, but all the future calculus classes as well. So here we're going to have the uv minus the integral of v du. Nope. All right. I'll just write a little dot right here instead. There. So once again, this is u v minus the integral of v du. The little arrows here again just mean this is uv, that's the first thing that you're going to write, and then this is going to go inside of your integral. This row here is going to go inside of your integral. If you want to think about that as a table. Cleaning this up, usually we write the x in front of the ln. And now you can see the benefit of choosing u equals ln, because now the derivative, the du that appeared inside of your new integral is 1 over x dx, and that 1 over x can simplify with the v, which is x, and it'll just turn into 1. So you can write this as 1 dx, or you can just write this as dx, with the understanding that there's a 1 inside. I'm going to leave the 1 out though, just because that's the form you'll usually see it. You want to get used to that. So the integral of 1, the antiderivative of 1, will be x, because the derivative of x is 1. And then at the end, we have a plus c. Great, so the integral of ln x dx is going to be x ln x minus x plus c. Who would know that the integral of such a simple function like that would be so complicated? But it was the same with secant x, as we saw in a previous packet. All right, again, you could check this by taking the derivative, and you'll get ln x in the end. Now, one thing is, it's a little bit weird because usually when we were doing the antiderivative, usually we were seeing ln of the absolute value of x's. But here, we never had to find the antiderivative of 1 over x, which would most generally be the ln of the absolute value of x. We never really had to do that in any of these steps here. The only thing we did was write uv, and u was originally just ln x without the absolute values. So I just wanted to point that out because sometimes it's a little confusing. Okay, so example 3 says find the integral of x squared e to the x dx. Now by our mnemonic, liate, what's going to be our choice of u? If you said algebraic functions, this polynomial x squared, that would be correct. The exponential is a bad choice for you. Bad. Nothing wrong with exponentials. They just don't make good choices for you. Okay, so we're going to let u equal x squared, and then dv is all the rest. I'm going to not write the u and the dv underneath for this one, but you can if you want to. Du will be 2x dx. V, we're going to integrate e to the x. We're going to find the antiderivative of e to the x, which is e to the x still. And now we're going to write up the right side of the integration by parts formula, which is going to give us x squared e to the x minus, and then we're going to have the integral of e to the x times 2x, the integral of e to the x times 2x. Now, since we're multiplying these together and looking ahead, I'm just going to write them in the order that we're used to seeing them. So 2x e to the x dx. There we go. Okay. Now, what we have is the power of x basically just went down by 1 by doing this integration by parts. We used to have an x squared, now we have an x to the first power. And that makes things a little bit simpler. Maybe if we do this again with this new integral, another integration by parts, maybe the power, maybe x will disappear altogether because we're going to take another derivative and you'll just get a 1 for the derivative of x. Or you can think if we let the u be this whole 2x, then the derivative of 2x will be 2. But the main thing is the x will disappear and our next integral will be even simpler. Let's do that off to the side. We're going to let u equal 2x. The dv will equal all the rest, e to the x dx. So we have du equals 2 dx, v equals e to the x. Now I'm going to open up some parentheses because this integral by the integration by parts formula is going to explode into 2 terms, the uv term and the integral of v du term. So open up some parentheses. If there's something in front, that's going to have to distribute to each of those 2 terms. Just like this negative will in a moment. I forgot to write these little arrows, so we're going to have uv minus the integral of v du. That's 2x e to the x minus the integral of e to the x times 2, which is 2 e to the x dx. Okay. Now, one last thing is we're going to integrate, so one last thing, not one last thing, a couple last things. So we're going to integrate 2 e to the x dx. That one we can integrate. The 2 can pop out. We just have the antiderivative of e to the x, which is e to the x. So that one, we're just one step away from finishing all of our integration. And actually, since we've finished our integration, let's celebrate by putting a plus c at the end. That's what you do when you have a general antiderivative like this. When you have this kind of integral, you're always going to have this little plus c at the end, right? Now there's one last step that we're going to take, which is to distribute that negative. That's going to flip the sign in front of that last integral that we got, that we evaluated. That's going to flip its sign, right? So you have the negative from that was in front of the first integral will distribute to the negative in front of the next integral, and so the next integral is actually going to have like a positive sign in front of it, right? The first integral is going to have a negative sign in front of its uv. The uv is talking about this 2x e to the x. And then the next the last integral is going to have a positive sign in front of its antiderivative. So if you kept on doing integration by parts, you might think like the signs are going to keep flipping and flipping and flipping if you kept doing integration by parts, because you'll have the negative sign distributing to yet another integral. So you have a negative and another negative, which would make the next integral a negative. So I just wanted to point this out because in a moment we're going to look at another method of doing this integration by parts, but in a more streamlined fashion, and that will be called the tabular method of integration by parts, or tabular integration as it's called for short. Thanks for watching, and see you in the next video.